A warm welcome to this tutorial entitled 4 Decades of Array Signal Processing Research and Optimization and Relaxation Technique Perspective. The rationale for this name is that we will present several known methods for direction of arrival estimation from a viewpoint that is a little bit different from the usual. Specifically, we will see how ideas from modern optimization play a role in constructing estimation methods. The tutorial is presented by Marius Pesavento and Minh Trinh-Hoang, both from the Technical University of Darmstadt in Germany, and myself, Mats Viberg, from Blekinge Institute of Technology in Karlskrona, Sweden. Before starting, I would like to mention the contributions from co-workers Christian Steffens and Yang Yang, both also from the Technical University of Darmstadt. And part of this work has been funded by the German Research Foundation under the contracts that you see here. So now I'll hide myself. We devote this tutorial to our former colleague and source of inspiration and knowledge, Alex Gershman. Alex sadly passed away, leaving a rich treasury of results, but still with so much left to do. We all miss him sorely, but we will never forget his enthusiasm and brilliance. Now, from a mathematical point of view, DOA estimation deals with parameter estimation from a rather general data model, which appears in several different application areas. Many of them do not even involve a sensor array explicitly, like harmonic retrieval and time delay estimation. And some of the classical applications are mentioned here, like radar and sonar, military and civilian applications. The goal can be to reliably resolve closely spaced sources and to suppress interference. Wireless communications and satellite communications, for example, to increase capacity and deal with interference. Radio astronomy, where DOA estimation can be used to generate high-resolution images, medical imaging, geophysical exploration, and so on. And some more recent applications are also listed in the bottom. Next, let me give a little bit of history. One may trace the origin of direction of arrival estimation to an invention from 1902 by John Stone, an American mathematician, physicist, and inventor. He patented the two-element array as shown in this figure, which could be used to determine the direction of incoming radio frequency signals. And the technique was later improved by several researchers and inventors, including Marconi. And in 2011, Hans G. Schantz published a nice overview of the history of RF-based direction finding. Now, obviously, the abilities to sample signals and use digital signal processing open up vast new possibilities. The number of applications grew, and one example is seismic applications for earthquake localization and oil exploration. In the late 70s, researchers like Ralph Schmidt and Bienvenu and Kopp started to exploit the geometry of the mathematical data model in a clever way, which led to the invention of subspace-based methods that have superior resolution capability, provided that the SNR and the number of data is high enough. Subspace methods attracted a lot of interest in the following decades, and several new methods were developed, and we will revisit some of them in this tutorial. But before going into mathematics, I want to give you an intuitive idea of the DOA estimation problem using figures. So assume that we have an array of sensors. Let's say it's electromagnetic antennas here. The signal is transmitted from some far-field source, and it's picked up by the antenna elements. And the difference in the path lengths to the different elements give rise to phase shifts between the signal at different antennas. So we collect these into vector that we call the array response. And it is illustrated using a certain color. So the phase shifts depend on the direction of the incoming source. So a source from a different angle will have a different color, basically, or a different signature, and so on. So sampling the whole field of view gives us a collection of array responses, each one corresponding to a different direction, illustrated by different colors in this picture. Now, suppose the array receives signals from different sources like this, again from the far field. We will assume linearity so that this principle of superposition applies. Then the measured signals, what we picked up at the array elements, will be a linear combination of all these propagation vectors or array response vectors. They're weighted by the source signal, and this source signal can be time varying if we have multiple measurements or snapshots. Now, the DOA estimation problem, it is to go backwards in this picture. So in other words, given this measured signal from the output of the antennas, try to figure out which of these columns or these array response vectors could have produced the measurement. We don't want to have more unknowns than equations, so normally it is required that the number of sources is less than the number of sensors. Several classes of DOA estimation methods have been proposed over the past 4 decades. For example, maximum likelihood, which is a general statistical estimation method, and spectral-based methods. There is always an interest to reduce the computational cost without sacrificing too much performance, and then some search-free methods have also been developed. What we want to do in this tutorial is to give insight into several of these methods from the perspective of modern optimization techniques. Now, maximum likelihood and other multidimensional search methods are based on more or less explicitly trying to reconstruct the measurement using candidate DOA parameters, as illustrated in this figure. So here are the 4 candidates from these. They form these array response vectors, and we try to match them with the data like this. So we have a reconstructed signal, and then this is the measured signal, and together it produces some measure of fit, which we call residual error here. A new set of parameters give a different residual error, and so on. The search continues until we found the optimum, the smallest possible residual error. And then we have our estimates. Spectral-based methods, on the other hand, they search for only one source at a time. So there is only one array response vector that tries to reconstruct the signal. So the basic beamforming method illustrated here ignores that there are several sources present, and it tries to fit the one source model to the data. That gives some residual error when we are here, and then we sweep over the field of view like this, all the way around, and all the time we measure the residual error. And when we are done, we locate the minima, local minima of this residual error, and those minima will be our estimates of the directions of arrival. The principle is very simple and computationally efficient, but it suffers from limited resolution capability. Now, a recent idea that we have presented tries to overcome the limitation of beamforming like this. So the received signal is again modeled as a superposition of several sources. but only one of them is modeled according to the array response structure. So if there are 4 sources, like in this picture, the remaining 3 response vectors, they are taken as general complex m-dimensional vectors, where m is the number of sensors. So again, trying to fit this model to the data produces some residual error, and we search the whole field of view like this, each time computing some residual error until we are done. And then the location of the minima will give the estimated dways. So this time, although it's similar to classical beamforming, this method will give much higher resolution, because the implicit multiple source modeling, which is done here, is able to cancel interference between sources from closely spaced dways. And this idea can be used to construct many different estimators, and we call this a framework partial relaxation estimators. So this tutorial should be useful for experienced researchers in the field, since we present known material in a different way. And also we can catch the interest of some of those who are new to the area. As previously mentioned, we revisit the DOA estimation methods using ideas from modern optimization, specifically problem approximation and relaxation techniques. We show how these ideas have always played an important role in deriving new algorithms, either explicitly or sometimes more hidden, as a consequence of another principle. So we will present new derivations of existing algorithms, specifically from the point of view of approximation and relaxation. And in particular, we will show how our new partial relaxation framework that I just illustrated is also based on approximation and relaxation. The tutorial is divided into 4 different parts, where this is the first, and Minh, Trinh-Hoang will do part 2, whereas Marius Pesavento will present parts 3 and 4. And together, these 4 parts can be grouped into the 3 headlines that you see here, where the first one provides some background material and an introduction to the problem of DOA estimation. The second part presents some of the most relevant estimators for this tutorial and revisits them from the perspective of approximation and relaxation. And finally, the third part is about performance bounds, and in other words, that means the best possible one can do with a given data model. So let us now take a look at the underlying mathematical data model that is used in this kind of problems. So we assume that n signals from far-field sources arrive at an array of m sensors, where m is greater than n. Far-field means that the propagated signals are plane waves. The array can be arbitrary. In this picture is linear. If the array is 2-dimensional, one can estimate 2-direction parameters, azimuth and elevation. Electromagnetic antennas may be polarization sensitive and give 2 outputs from each location, but here we only look at the case of 1 output for each sensor. And we also ignore things like mutual coupling and similar. So the received signals are assumed to reside at some high carrier frequency. And before sampling, they are converted to baseband using in-phase and quadrature phase sampling to give a complex baseband signal denoted S of t in this figure. The bandwidth of the baseband signal is assumed to be much less than the carrier frequency in this sense, shown here. Also, the physical size of the array is such that the baseband signal can be assumed to be constant throughout the propagation across the array. So we need one more assumption, which is already mentioned, that the sensors and the receiver equipment all operate within their linear regime, Then the sample sensor signals will be a superposition of the contributions from each signal source. And under the mentioned assumptions, the sensor array output can be well modeled by the familiar equation shown here. X of t denotes the complex baseband sensor output at time t, and the matrix A of theta contains the steering vectors as its columns, and the vector S of t has the corresponding signal waveforms as components. The vector N of t represents additive noise, which takes into account anything in the received signal which does not emanate from the source signals. The matrix A of theta is M by N. Its columns are the steering vectors. A of theta k, where theta k is the kth component of the DOA parameter vector theta. The steering vectors depend on the array geometry, and for a uniform linear array, it has the form shown here. In general, the array manifold is defined as the span of steering vectors as the theta varies over its definition region, which is in this case taken as 0 until 180 degrees. So again, looking at the array measurement model, the components of the M vector X of t are the outputs of the respective sensors. The components of the N vector S of t are the waveforms from each signal source. The components of N of t represents the noise in each sensor. And each are sampled at an arbitrary time instant t. When deriving optimal methods and deriving the statistical performance of these, we need to make assumptions about the noise characteristics. And we will here adopt the most commonly used model, which is that N of t is a spatially and temporally wide circular Gaussian random vector. Its mean is 0, and the common variance in each sensor output is nu. And the noise is assumed to be independent from sensor to sensor. We assume that t-independent snapshots of the sensor outputs are available, or sometimes t is assumed to be very large. The measurements are collected as columns in the received signal matrix X, which is M by t. And similarly, we construct the source signal matrix S and a sensor noise matrix N. So we are given the data matrix X and the data model shown here. The objective is to estimate the DOA's theta. In this presentation, we will assume that the number of sources is known, although estimating N is in itself an important and quite difficult problem. Regarding the signal waveforms, there are basically two major options. In the so-called stochastic model, S of t is modeled as a complex circular Gaussian random vector, just like the noise. It is zero mean, and the covariance matrix is denoted P. In most cases, we assume that P is positive definite, which means that the source signals are not fully correlated, like this. Under this model, the measurement vector X is also IID circular Gaussian. It will then be fully characterized by its covariance matrix R, which is given by this model, APA Hermitian plus nu times identity. And the covariance matrix is parameterized by the DOAs, by the signal covariance matrix P, and the noise variance nu. The other option is that we consider S of t itself to be parameters. In other words, they are deterministic quantities. And we term this model the deterministic model. Then X is no longer zero mean, it has actually a mean which is A of theta S of t, and the covariance matrix of X is nu times identity. And in this case, the parameters are characterized by theta again, the signal waveforms, and nu, the noise variance. So an interesting observation is that in this case, the number of parameters is proportional to the number of observations, t, because of S. This is a little bit problematic if we are interested in asymptotic properties as the number of snapshots grow large, because then also the number of parameters grows large. The final player we need to introduce is the sample covariance matrix, R hat. In the stochastic model, this will be a point estimate of the covariance matrix of the array output. It is the time average as an estimate of the ensemble average. But in the deterministic model, we may just call it the sample correlation matrix of the data. So given the data model, is now time to give a review of existing DOA estimators. I will start with optimal maximum likelihood methods and then some of their approximations. So we are given a random stationary process X, and it is observed at t time instances. And we have this multivariate PDF F, which is parameterized by some parameter vector alpha. And inserting the data samples X of t instead of the random variables gives us the likelihood function, F of X, like this, given alpha. And the maximum likelihood estimator is the one that maximizes this likelihood function. This is natural, since this is the value that makes observed data as likely as possible. But ML has an even more important property. Under mild regularity conditions, it will asymptotically achieve the CRB. Asymptotically can be thought of as up to first order. In other words, whenever the data contains enough information so that the estimation variance is small. This can be if the number of samples is large, if the number of sensors is large, or if the noise variance is small. So although ML is the optimal estimator, its computation is not always simple, but sometimes one can partition the parameter vector alpha into two parts, such that it is possible to find a closed form solution with respect to one part. So let's assume that alpha has alpha 1 and alpha 2 as the parts. Then we can write the maximization problem with respect to alpha as 2 maximization. First an inner maximization with respect to alpha 2, and then everything maximized with respect to alpha 1. So if it is possible to find a closed form solution with respect to alpha 2 given alpha 1, we can take that value and substitute it back into the inner optimization, and that gives us the maximization with respect to only alpha 1. So that maximization, the final one, will be of less dimension, although it may also sometimes lead to a more complicated parameterization with respect to alpha 1. Coming back to our two models for DOA estimation, let's first look at the deterministic signal model. Maximizing F is the same as minimizing the negative log likelihood, which is shown at the bottom here. It is derived from the Gaussian multivariate Gaussian likelihood function shown here. We recognize this as a straightforward least squares problem with respect to S, and in fact it is also possible to find a closed form solution with respect to the noise. So for fixed DOA parameters theta, the minimum with respect to S, the maximum likelihood estimate with respect to S is given by this, and the noise estimate is given by this. Here A dagger is the Moore Penrose to inverse, and the PI perp and the PA are shown here. P sub A is the projection matrix onto the range space of A, and PA perp is the projection matrix onto its orthogonal complement. So plugging these explicit estimates back into the likelihood function gives us this concentrated negative log likelihood function. Therefore, the DO estimates can be computed like this by minimizing this quantity. The criterion function has a nice geometric interpretation. So R hat, the trace of R hat is the total power in all sensors. But before taking the power, we should project the covariance matrix onto the orthogonal complement on the range base of the steering vectors. And when the parameters are correct, this projection will remove any signal component from the sample covariance matrix, leaving only the noise part. So thus, the smallest value of this criterion, the total power, should be achieved when you remove as much as possible of the signal, only the noise is left. So this projected power will be a good indicator of how the parameter vector matches the true parameter. So deterministic maximum likelihood minimizes this function here, which is proportional to the negative log likelihood. In general, it's a highly multimodal function, which means that it has many false local minima. Some may have a value which are close to the optimal values, to the global optimum, which makes it computationally costly to perform the optimization. For a full search, the complexity grows exponentially in the number of sources, and it becomes intractable for n larger than 3. And in practice, it may be too costly even for n equal to 2. So this plot gives an illustration of the deterministic maximum likelihood criterion function. In this case, the array is a 10-element standard uniform linear array, and the true DOAs are 10 degrees apart. The signal-to-noise ratio is 10 dB, the number of snapshots is 100. And the color indicates the value of the criterion function for different values of θ1 and θ2. And the plot is symmetric, as you can see, since the ordering of the parameters is irrelevant. Each circle in the plot is a local minimum. And the deepest ones, given by crosses, they appear, or the deepest values of the local minima appear along the values where one of the parameters is close to its true value. And the global shape, as we see here, is quite far from a convex function, although locally around the true minimum, of course, it can be approximated by a quadratic. Thus, if one can start close enough, one can do a Newton search and arrive at the global optimum. The question is how to get close enough with some guarantee. This is, in fact, where approximation and relaxation techniques come into play. Turning now to the stochastic data model, it looks like this. And here we need to parameterize the signal covariance matrix P, and it is done using some vector little b p. So we have theta, p, and nu. The likelihood function is again obtained from the multivariate Gaussian, as shown here. Now the negative log likelihood is this one. And also in this case, one can derive explicit solutions for the nuisance parameters, namely the noise variance and the source covariance matrix. Substituting these back into the negative log likelihood function gives the stochastic MLDOA estimator as defined at the bottom of the slide here. Again, it's an n-dimensional criterion function, and there is little hope of finding an explicit solution with respect to theta. And also in this approach, may lead to unacceptable computational complexity. So let us now turn to another approach which exploits the geometry of the data model. The idea of so-called subspace methods is that the array has a low-rank signal component. The covariance matrix has a low-rank signal component APA emission, plus a matrix proportional to the identity. It's low rank if the number of sources is less than the number of sensors. So if we perform the eigendecomposition of the array covariance matrix and sort the eigenvalues, we find that the smallest eigenvalue is equal to nu, and it is repeated n minus m times. And these we call the noise eigenvalues. The remaining eigenvalues, they are all larger than nu. We call them the signal subspace eigenvalues. Together, the signal subspace eigenvalues span the same space as the steering matrix A, and the noise eigenvectors corresponding to this eigenvalue, they are all orthogonal to the steering matrix A. So let us now collect all the signal and noise eigenvalues and the eigenvectors into matrices as shown here. Give you some time to read. Now, eigenvectors to Hermitian matrices can always be chosen orthonormal. So let us assume that U is unitary. As I previously mentioned, the signal eigenvector matrix and the steering matrix span the same space. And then there is a matrix K, such that U sub S is AK. The noise eigenvector matrix is orthogonal to the signal eigenvector matrix, therefore also to the steering matrix, A of theta, like this. So either of these properties can be used to construct an estimator, which may call the signal subspace method from this relation, or a noise subspace method from this relation. Of course, in practice, we don't have access to the true covariance matrix, and instead we perform the eigendecomposition of the sample covariance matrix, R hat. We use the same notation, but with a hat for estimated signal and noise eigenvalues and eigenvectors. And we collect them into similar matrices as before. Now, let us for a moment look back into the deterministic maximum likelihood cost function. This can be derived as the least square solution to the formulation at the middle of the slide. Substituting the least square solution back into the least squares criterion gives the formulation at the top. And that the idea is now to mimic deterministic maximum likelihood by replacing the data X by the signal eigenvector matrix US hat. To be more general, a weighting is applied, basically to acknowledge the fact that the estimated eigenvectors may not be equally accurate. In fact, eigenvectors corresponding to eigenvalues close to the noise variance can be very imprecise and should be given a low weight. Since the signal eigenvectors span the same space as the steering matrix, a natural criterion for finding DO estimates is the one which we see here. And substituting the least square solution for F gives to the weighted subspace fitting criterion, which is at the bottom of the slide here. So, weighted subspace fitting DOA estimates are given by minimizing this function here. Again, this requires an n-dimensional nonlinear and non-convex optimization. However, if the number of sources is much smaller than the number of sensors, computing the WSF criterion is less costly than for the two ML criteria. Also, WSF can be related to the two maximum likelihood formulations used by using different weighting matrices. And the one shown here gives the smallest possible estimation error variance, and it also gives estimates that are asymptotically identical to stochastic maximum likelihood. There's another choice that makes WSF asymptotically identical to deterministic maximum likelihood, but that is not the optimal choice. The difference is often negligible, especially for high SNR. And the final class of methods considered in this part of the tutorial is the so-called covariance matching techniques. The idea is very simple. While deterministic maximum likelihood involved the least squares fit of a model to sensor data directly, covariance matching will do the same, but it will match a model to the covariance matrix in the least square sense, like this. So this is a general COMET formulation, where R hat is the sample covariance matrix, and APA emission plus nu times identity is its model. And the matrix W is some general weighting matrix, which is a user's choice. If you choose the identity is of course the easiest. But there is also a choice which is asymptotically optimal, like this, and it makes the comet achieve the stochastic Raman lower bound, which means that it also gives minimum variance estimate asymptotically. Now, the nice thing about the covariance matching model is that it is linear in the signal covariance matrix parameters. And if we vectorize the covariance matrix, we can explicitly write it like this, where gamma contains both the noise power and also the signal covariance. So then we can arrive at the linear least squares formulation with respect to these parameters, nu and p. And we can concentrate the comet formulation again, just like the other maximum likelihood methods. And we arrive at the search, which is only over the theta. Actually, the comet formulation has another constraint, which is that the source covariance matrix should be positive definite. So to arrive at this formulation, one has to relax that constraint, which is the first example of relaxation. We will apply it in a much more general context later in the tutorial. So, in concluding this part of the tutorial, I will demonstrate the performance of the variance estimators that we have shown so far using computer simulations, and they will also be compared to the ultimate performance given by the Kramer lower bound. And here we look at the case of two uncorrelated source signals arriving at the 5-element standard uniform linear array. One is from broadside and the other one is 10 degrees apart. The number of snapshots is 200. And the plot shows the root mean squared error of the DOA estimate as a function of the signal to noise ratio in decibels. And in this case, the CRB is almost a straight line, the black curve here, in this case. And the optimal estimates achieve the Kramer lower bound over a certain SNR threshold. And in this case, deterministic maximum likelihood and WSF have the best threshold performance in that they achieve the CRB at the lowest SNR value, followed by stochastic maximum likelihood. And the Comet method, in this case, was implemented without the constraint on the signal covariance matrix. It suffers from the presence of outliers, even at high SNR. But the plot also shows the root mean squared error if you remove 5% of the outliers, and then also the Comet estimates come very close to the CRB at high SNR. Or actually, you remove 5% of the estimates, the worst ones. So next, we look at the case where the two signals are highly correlated, 99% correlation. Otherwise, the same scenario. In this case, stochastic maximum likelihood shows the best performance, threshold performance, followed by WSF and Comet. However, the Comet estimates have an error floor indicating that they will not give the correct values even for infinite SNR. The DML method has a higher resolution threshold, and it also does not quite achieve the stochastic CRB as shown in this picture. So this concludes part 1 of this tutorial, and it is time for a break. And right after the break, Minh will continue with the second part. Thanks for listening.